Okay, so hi, welcome to this next video on linear programming. So in this video, we're going to just be discussing a handful of topics related to extreme points that somehow just haven't come up so far in our discussion of these things, in a natural way at least. And it would be good to address these features of extreme points before leaving the topic entirely. So I thought I'd include them in a final video. And actually, it'll be related to the previous video, and in a way that it'll actually probably shed some light on some things that it'll give some context to what was going on in that prior video where we did this correspondence of extreme points of an original linear program to the SEF version of the linear program, and how the simplex algorithm then worked geometrically. So let's start there. Actually, let's talk in a bit more generality about what was going on in that video, and then we'll get to these various features of extreme points that'll become relevant. So, what happened in that video is that we started with the linear program that was not necessarily in standard equality form, and then we wanted to run the simplex algorithm on it so that we could then show that the simplex algorithm was going from corner to corner, or extreme point to extreme point of the associated polyhedron. But in order to run the simplex algorithm, you need to be in standard equality form. So what we did was we converted and we put it this linear program in standard equality form, in the sense that we created an equivalent linear program, which was in standard equality form. And the polyhedron are not the same, though, so we had to establish that there was still a bijective correspondence of these extreme points. The way that ended up working out was that there's these three separate equivalences. There were the basic feasible solutions of the linear program in standard equality form, and we already knew that basic feasible solutions and extreme points were the same thing. So these were the same as the extreme points of that linear program in standard equality form. But then, in addition to that, the extreme points of that linear program in SEF form were in bijective correspondence with the extreme points of the original linear program. And so that was why the simplex algorithm, it was running on the SEF version of the linear program, so it was iterating over basic feasible solutions there. But that in turn, if you go through this set of equivalences, that in turn meant that it was actually iterating over extreme points of the original linear program. And that was the geometric insight that we were able to have. But the question now is that, does this correspondence have to hold? Because that was an example, but does that hold for any linear program? You just take the standard equality form version of the linear program, and then this equivalence of basic feasible solutions of the SEF version, extreme points of the SEF version, and extreme points of the original. Does that hold? Well, I mean, first of all, the first equivalence does always hold. I mean, we already just know that for standard equality form, basic feasible solutions and extreme points are the same thing. That's just always true. But it's the second equivalence. Do extreme points of the linear program in SEF form correspond to extreme points of the original linear program? Does that have to hold? And the answer is no, not in general. So just for a very small example here, imagine this linear program where it's just in one variable. So we'll just call that single variable just x. So we're maximizing, let's just say 3x, such that there's actually no constraints at all. But I just explicitly wrote that x was free, or in other words, x is just a real variable. That's not a constraint, really. That's just saying that, it's just explicitly saying that there's no constraints. And so there's no constraints whatsoever. X is a free variable. Well, how do you convert that into standard equality form? What you do whenever you have a free variable, this is just the standard thing to do, is you just replace it by the difference of two non-negative variables. So x plus and x minus. So x becomes x plus minus x minus. Those are the superscripts there, x plus minus x minus. So you see that it's 3 times that. And now those two variables, x plus and x minus, are both non-negative, because I can write any number as the difference of two non-negative numbers. And so that's why that works. And so this is standard equality form of in standard equality form because there's just no equality constraints and all the variables are non-negative. But the thing is that the extreme points don't correspond because in the original linear program there are just no extreme points at all because the polyhedron is just the real line, and so there's no extreme points on the real line. And here the two variables are x plus and x minus. So there is exactly one extreme point because it's just the positive orthant here, or positive quadrant. In this case, it's a quadrant because there's two variables, and so it's just the origin. It's the corner point. There is the extreme point. So it's where both x plus and x minus are 0 at the origin. So that's an extreme point. So you can see that there's no extreme point in the original linear program, and there's exactly one extreme point for the SEF version. So there can't possibly be a correspondence of extreme points because there's a different number. There's none here and there's one here. So this correspondence that happened in the prior video where there was a bijective correspondence between extreme points of the original linear program and extreme points of the SEF version, that doesn't always have to hold. So why did the correspondence hold in our example from the prior video? Well, there's at least a sufficient condition that I can give you for now, which is the nice thing that we had was variable non-negativity. This is the setup that we had from the prior video. We had something of the form max C transpose X for some objective function, some less than or equal to constraints, and then we also had variable non-negativity constraints. So we could have absorbed those constraints into the matrix less than or equal to constraints by just flipping the greater than or equal to a less than or equal to by multiplying by -1 and just putting the corresponding matrix constraints into this overall matrix A. But it's probably better that we explicitly write them out like this because they're related specifically to the variables, so they're kind of special in that way. So just all the other constraints are captured by AX less than or equal to B, but specifically for the variable non-negativity constraints, we write those separately. And that's what we had in the prior video. We had something of this form where we guaranteed these variable non-negativity constraints. We had those, and so that is what I'm claiming to be a sufficient condition in order to have this correspondence of extreme points of the original linear program to the extreme points of the SEF version of the linear program. Why? Well, because what happens is, how do you go to the SEF version of this linear program? What you do, it's the same objective function, but you add slack variables now. So instead of AX less than or equal to B, now it's AX plus S is equal to B. So S is a vector of slack variables, and I have one for each constraint, so that for each constraint over here, we had something that had an upper bound of a B component, and now by adding a slack variable, we attain that upper bound of the B component. Since we're attaining an upper bound, we were adding something non-negative. So the x's are the same from before, and then the s's are the slack variables. They're more variables that we're introducing, and they're also non-negative because we're adding something non-negative to attain an upper bound. So this is certainly in standard equality form then, because it's equality constraints. The matrix isn't A anymore. It's A, and then actually there's an identity matrix implicitly in front of the S vector here. But anyways, it's still matrix equality constraints, and then all the variables, the x's and the s's, they're all non-negative. So then this is standard equality form. So that's the conversion that we did. This is just the generalized phenomenon happening here. And then, well, if I have the variables x, what do they correspond to in the SEF version? Well, it's x and then the slack variables s, where s is completely determined. It's b minus ax. So we already know what x is from the original linear program. That's this x here as well. And then so b and a are given data, and an x is given to us. That's what we're starting with. So then s is completely determined. So that tells us overall what this overall vector x with the slack variables s as well is. And that's the variable vector corresponding to the SEF version. And then vice versa, if you're going from the SEF version to the original linear program, if I have the x's and the s's and I'm just going to the original linear program, I just keep the s's. So x is just projecting this x and s overall vector onto the first n components, onto Rn, which is it's just keeping the x components and forgetting about the s components because we don't use slack for the original linear program. And then what we said in the prior video, and then this is true in this general format, is that x is feasible if and only if the corresponding x with the slacks is feasible for the SEF version of the linear program. And then there's also this if and only if condition for the extreme points. X is extreme if and only if if and only if the corresponding XS in the SEF version is also extreme, and vice versa. So those two conditions were true in that video that we did, and they're true in general when we're in the situation of variable non-negativity. So why is that true? Well, for the first condition, the feasibility, if and only if the other is feasible, let's just assume that x is feasible. So we know that for the original linear program, so we know that ax is less than or equal to b, and x is non-negative. Well, then why does that tell us that x with the associated slack variables s, that's feasible for the SEF version? Well, because a times x plus s, well, we know what s is. We can just replace it with what we know it is. It's determined to be b minus ax. That's what it is in general. So we have ax plus b minus ax. The ax's cancel, and we just left with b. So ax plus s does indeed equal b. And then since ax is less than or equal to b, in other words, that's saying that b minus ax is non-negative, and that's what s is. S is b minus ax, so s is non-negative. So here you go. You have the matrix equality constraints, A appended by an identity matrix, because implicitly we have, when we're adding slack variables, we're adding identity times slack variables, just so we have a formal matrix here. But anyways, we have it's matrix equality constraints for the variables, the x's and the s's, that equals b. So here we're equaling b, we're attaining that upper bound, and then the variables x and s are non-negative. So matrix equality constraints are satisfied, variable non-negativity constraints are satisfied, therefore the xs is feasible for the SEF version. And then in the other direction, I mean, you just basically do the algebra in reverse. I mean, I just, if I'm starting with the x's and the s's satisfying this, now I'm just dropping the s's, and since s is non-negative, then if we're satisfying with equality here, and I'm dropping something that's greater than or equal to 0, then a times x without the s's added on is then less than or equal to b. And then we already know that the x was non-negative from before, so it's non-negative now too. So that's for the feasibility portion. Now for the extreme point portion, if we're, so that's part 2 here. So part 2 is saying x is extreme if and only if xs is extreme for the linear program, the SEF linear program. Okay, so why is that part true? Well, let's just assume that x is not extreme, and then we'll show that the xs is not extreme for its linear program as well. Well, if x is not extreme, then I can write it as being strictly between x prime and y prime for some points x prime and y prime in the polyhedron associated to the original linear program. And so I have lambda x prime plus 1 minus lambda y prime for some lambda strictly between 0 and 1. That's just what it means for x to not be extreme. And so then in turn, what is xs? So I know what x is. We just figured that out. I mean, well, we just, by definition, this is what it can be written as. So we replace x with that. And then s, we know that that's b minus a times x. And again, we can just replace x with this lambda x prime plus 1 minus lambda y prime. So that's what's happening here. So b minus a times that for that bottom component part. And then we can just write b. It's better written as lambda b plus 1 minus lambda b. You can see that that's just basically an expansion. If we simplified that back down, we would just get b. But it's better to write it like this because in the next line, we can see that we have lambda x prime plus 1 minus lambda y prime. That's the top half of the vector. And then for the bottom half of the vector, we have lambda times b minus ax prime plus 1 minus lambda b minus ay prime. Look, for the x prime part, we have lambda times the x prime part for both the top half and the bottom half. And for the y prime part, we have the 1 minus lambda factor scalar in front. And what is b minus ax prime? That's the slack that's associated to x prime. And similarly, b minus ay prime is the slack associated to y prime. And so yeah, so that means I can write this as lambda times this vector x prime, and then the slack associated to x prime. That's what this notation is, s x prime here. That's b minus ax prime, just by definition. And then plus 1 minus lambda times y prime, and the slack associated to y prime. So yeah, and we know that that x prime and y prime were feasible for the original. So then x prime sx prime and y prime sy prime are feasible for the standard equality form. And so since these are feasible, and it's a linear combination of those given by lambda plus 1 minus lambda for those parts, that means that xs, we just did this computation, and it equals this. So it can be written as being strictly in between x prime sx prime and y prime sy prime. And so that means that xs is not extreme. And then on the other hand, if we just wanted to, if we assumed that from the start, that xs could be written in this way, then we can do the algebra in reverse. We can go from bottom to top, and that would just show us that then the original x is not extreme, because well, we just know right away that in particular lambda x prime plus 1 minus lambda y prime equals x, and that means that x is not extreme. So all that is to just say, this is simple algebra. It kind of, me saying it in words is making it sound more complicated than it really is almost. So I don't want to dwell on it. The entire point is just to say that if one is not extreme, then the other is not extreme as well. Or in other words, if one is extreme, then the other is extreme as well. So it was no coincidence for that one example. When you have variable non-negativity, you get this correspondence of extreme points for the linear program and the standard equality form of the linear program. You get that correspondence of extreme points. So what are the consequences of that? What can we deduce from all that? So what's a nice fact? It's this. If I have given for every non-empty, of course, has to be non-empty polyhedron of this form, where we have less than or equal to constraints, ax less than or equal to b, and then we definitely have variable non-negativity constraints as well. So if it's a polyhedron of that form, so it lives in the positive orthant, right? That's what it means for x to be non-negative. Anyways, it's just, okay, so we have variable non-negativity constraints and then some other less than or equal to constraints. Every polyhedron of that form has an extreme point, guaranteed. And why is that true? Because it's just a corollary of what we just talked about. We have this polyhedron here, given here, and then you can convert it. So it's the polyhedron associated to some linear program. So we can convert to SEF form, and since we have the variable non-negativity here, that definitely means then that when you look at the extreme points of the polyhedron for the SEF version, that definitely then bijectively corresponds to the extreme points of the original polyhedron. And since we know for sure that the SEF version does have extreme points, because that's the same thing as saying that the linear program has basic feasible solutions, and we already know that that's true. We proved in a prior video that every linear program in standard equality form has a basic feasible solution. So then the associated polyhedron have extreme points, and so and then we have this correspondence from extreme points of the SEF polyhedron to the original polyhedron, and so that gives us that there exist extreme points of the original polyhedron. And that's coming from the fact that we have this variable non-negativity. So that's what we were just explaining above, and so we deduce this as a consequence of what we were just talking about above. Okay, now that's guaranteed to happen when we have this variable non-negativity here. But what about if we aren't sure whether we have variable non-negativity? What if we just have the less than or equal to constraints? Maybe the variable non-negativity is part of those, but also maybe it's not. It's not guaranteed anymore. So when exactly does a polyhedron of this form, it's just the x's that satisfy ax less than or equal to b, when does that contain an extreme point? So now we're not saying that x is non-negative, it just satisfies ax less than or equal to b. That polyhedron, when does that contain an extreme point? Because we know that polyhedron, when we enforce x non-negative, they definitely have an extreme point. But when we drop that condition of x non-negative, when does that polyhedron have an extreme point? That's the question we can answer. Well, first of all, we already know that there's one characterization in terms of the rank of matrix of tight constraints, right? I can test any individual point of this polyhedron by looking at the matrix of tight constraints and seeing if it's full column rank or not. But I don't want to have to test each individual point. I'm just looking for a feature of the overall polyhedron and to describe whether or not the overall polyhedron has an extreme point or not. And I don't need to know which point is extreme. That's not the question. It's just, does there exist one? Is the question. So here is a characterization of that. The polyhedron given by the set of points that satisfy ax less than or equal to b. So again, there's no non-negativity necessarily here anymore. But a polyhedron like that contains an extreme point if and only if it does not contain a line. Okay, so a line, as we defined in a previous video on when we first talked about convexity. Anyways, the idea is that these two things are incompatible with each other. Extreme points and lines cannot exist in a polyhedron simultaneously because a line is infinite, and there's some sort of sense of boundedness of a polyhedron in some way. But the idea is that either your polyhedron will have a line or it will have an extreme point, but never both, and always one or the other. So you can kind of here's just a rough idea with this picture right here. Like if this was the polyhedron in the shaded black part, there would be an extreme point because it would be this corner point right here. But if we also had a line, let's say this green line, you can see that actually we can't contain the entire line because it must stop when it hits this wall here. If it kept going, then we'd be outside the feasible region. So the only way to make that work is if we kind of stretched this boundary downwards, and then we had a line that went parallel to the boundary, because this would kind of flatten out. The black boundary would, instead of being two distinct segments, it would just kind of be one straight segment that would go infinitely, and then we could have a line that was parallel to that, and that would be contained in the polyhedron. But then that polyhedron, since we flattened out the boundary, it no longer has any extreme points. So as soon as you get a line, you lose the extreme point. So that's kind of the rough intuition for why only one or the other can exist. But we can prove it as well. So let's just take a look at a proof of how that would work. So we're trying to prove that if our polyhedron contains an extreme point, then it does not contain a line, and vice versa. So first, let's assume that the polyhedron does contain a line, and let's show that it does not contain an extreme point then. So if it does contain a line, so let's say it's like this, x bar plus td. So x bar is just some point in the polyhedron, and then we're traveling in the direction d. And t is a scalar that goes, it's for all t and r. It's infinite, corresponding to the fact that a line is infinite and goes infinitely far in both directions. And it's in the direction of d here. Okay, so if this polyhedron contains this line, then what that means is that this x plus td, when a multiplied by that, is less than or equal to b. All these, it satisfies the constraints. So a times this, I can distribute the a in, and I get ax bar plus tad is less than or equal to b. That's because we must satisfy the constraint to be in the polyhedron. And then I'm just going to isolate this part, the TAD part. So we have TAD is less than or equal to B minus AX bar. But T is infinite. Well, I mean, what I mean is it's ranging over all the numbers. So if T is some fixed number, I can also change it to be the negative of that. And that's another valid value of T that has to satisfy this constraint. So not only does TAD have to be less than or equal to this right-hand side, but so does minus TAD, because we have to go. We're going in both directions of the line. So yeah, so minus TAD is less than or equal to b minus ax bar for the same reason then. But remember that so one of these is going to be positive and one's going to be negative, or they're both zero. But let's assume one's positive and one's negative. So let's just say the top one's positive, for instance. If it wasn't, then the bottom one is. But let's just assume without loss of generality, it's the top one. The right-hand side is an upper bound on that, and it's fixed because x bar is a given point. A and b are data originally given to us, so this is a fixed right-hand side. But t is a scalar, then we can scale it as large as we want, and so that we can grow this left-hand side as high as we want. So this goes to infinity, but this is a finite number on the right-hand side. So how could it possibly, how could it be possible that this bound is satisfied in that case? Well, there's only one way to resolve that, because it's a contradiction otherwise, and we haven't assumed anything for a contradiction. So we can't have a contradiction. The only way to resolve that then is that a times d is actually the zero vector. So that way, when you scale either by positive t or negative t, it's the sign doesn't change. It's always zero, and no matter how large you make t, you're just scaling zero actually. So you'll still satisfy the bound. So this we have a times d is the zero vector, or in other words, d is in the null space of the matrix A. So whenever your polyhedron contains a line and it's going in this direction d is actually a null vector of the matrix A, in fact. So what that means then is, since we have a non-trivial null vector of the matrix A, there's something in the null space, the rank of that matrix must be strictly less than n in that case, because it can't be full column rank. If it were, then we wouldn't have anything in the null space. So the rank is strictly less than n, and so that in turn means that no matter what point x you pick, so for any point x in the polyhedron, there's an associated matrix of tight constraints. Maybe there's no tight constraints, in which case this is just kind of a vacuous condition. But at least for all the points where there are tight constraints, A equality is a well-defined matrix. But it's a submatrix of A. And since A itself, the rank was already strictly less than n, then the rank of A equality for all of those tight matrices, they're all strictly less than n, because the rank's only going to go down when you take a submatrix. So that's for every point x in the polyhedron, and we already have this characterization that a given point in the polyhedron is extreme if and only if the rank of matrix of tight constraints is full column rank. So the rank attains full column rank. So it's rank n. But here we've just shown that since the rank of the overall matrix is strictly less than n, the rank of all these matrix of tight constraints for all these points x in the polyhedron, all of them are strictly less than n. So none of those points are extreme. So x is not extreme for all x in the polyhedron, and so in other words, there does not exist an extreme point in the polyhedron. So we just proved that starting from the fact that the polyhedron did contain a line, that line had to move in the direction of a null space vector, and that guaranteed us that the rank was too small. The rank of the matrix was too small, and that meant that there were no extreme points. So that's what just happened there. So lines mean there's no extreme points. Now, on the other hand, what if we assume that there's no extreme point? Can we show that there actually is a line in that case, so that exactly one of the two things is true? So if there's no, and we can. So if there's no extreme point in P, we can show that there must be a line in P. And the way you can do that is you take a point x in the polyhedron, and if it's not extreme, well, we're assuming that there's no extreme points in the polyhedron. So x, no matter which point x you took, it's not extreme. So what does that mean? Well, it means that there's some direction d1 vector in Rn, such that when you perturb x in the direction of d1, so x plus or minus t d1, that's in the polyhedron for sufficiently small t. So maybe for very large t, if you do a very large perturbation, that's no longer in the polyhedron. But because it's not extreme, as long as you do a small enough perturbation, all the points on that in that perturbation will be in the polyhedron. So x plus or minus TD1, that's the perturbation. All those will be in P for small enough t. Okay, so there's two things that could happen. So case one, actually, it doesn't matter how large the perturbation is. That's a possible outcome. Or in other words, x plus or minus TD1 is in the polyhedron for all t. That would mean that the polyhedron contains a line. It's the line that is in the direction of D1 here. So then we'd be done because we've just found a line. But the other thing that could happen is that that's not the case, that we can only push so far in this direction, plus and minus D1. And so that's the other possibility. So possibility two, there exists some maximum amount that we can go in the direction of D1 by, which, so we can scale that only so much. So we can increase t only so much. So there's some value t1 such that once you go so far in the direction of d1, so then x plus t1 d1 activates some constraint. So we start at x, and we go in this direction of d1 scaled by some amount, and at some point you hit some boundary. And if you go any further, you're going to violate a constraint because you're crossing over the boundary, so you can't. So now you've activated it. You now have an active constraint at this point when you've gone this far. I said x plus t1 d1. It could have been x minus t1 d1 because it is x plus n minus. But I'm just going to assume it doesn't hurt. Just without loss of generality, you can just assume the plus case because otherwise we're going to get some messy notation. So we'll just assume the plus case. So when you go x plus t1 d1, you run into a boundary and you activate a constraint because you're on a boundary. So that's the other possibility that can happen. So in that, we're still in this possibility where we're just, because we still haven't found a line in that case. So we still know we're in the polyhedron as long as we don't go past the boundary though. So x plus t1 d1 is in the polyhedron, but the polyhedron has no extreme points still. So this is not an extreme point. So we can just do the same thing that we did before really. Since it's not an extreme point, there is guaranteed to be some vector d2, some direction d2 in Rn that's not in the span of the first vector d1, such that this point that we're now at, which is x plus t1 d1, and then we perturb that point by plus or minus td2, that's in the polyhedron for small enough t. Okay, so now t1 is a fixed value, right? So the only t that appears in this is right here, and so d2 is definitely not in the span of d1 because first of all we know it has to exist because it's not extreme. This point is not extreme, so we have to be able to perturb in some direction, and that direction cannot be in the span of d1 because if it was, that would have meant that we could have gone further in the direction d1 than we already did, but we've gone as far as we possibly could. So we can't go any further in that direction. So we have to be outside the span of that. So d2 is not in the span of that, and yeah. So now it's just kind of the same thing all over again. We're just either there's two cases. Either this point x plus t1 d1 plus or minus td2 is in the polyhedron for all t in reals. That's a possibility, and if that happens, then P contains a line. We've just found a line. It's this point x plus t1 d1, and then you go in the direction d2, infinitely far in both directions. That's a line in the polyhedron. So that could happen, and if that's the case, then we're done. We found our line. Or the other case, just like before, is that there's only so far you can go. So there's some value t2 such that you can only push t so far, so that x plus t1 d1 plus t2 d2, you only can go that far, t2 distance in the direction of d2, and then that'll activate another constraint. Okay, so because if you go any further, you're going to be on another boundary. You're already on another boundary, and if you go any further, you're going to cross over and violate a constraint. So this is as far as you can go. So you're on a boundary, and it's a different boundary from before because we were going in a different direction now, and so we've activated another constraint. And so, following this line of reasoning along. So okay, so again, it's just the same thing all over again. This point that we're at, it's still in the polyhedron, and there's no extreme points in the polyhedron, so this is definitely not extreme. So there's some direction d3 that we can travel in, and we can perturb this point in the direction of d3, since we're not an extreme point. And that direction d3 is not in the span of the original directions d1 and d2 of these prior directions d1 and d2, because if it were, then that means we've moved in some non-trivial amount in the directions of d1 or d2, and if we did that, then we would have crossed over the boundary, and the boundaries that we ran into when we traveled in those directions already. So that can't happen. So we can't be in the span of those vectors. So this d3 is guaranteed to exist, and it's also guaranteed to not be in the span of the prior directions. So so we have this point, x plus t1 d1 plus t2 d2, and now we're perturbing it in the direction of d3. So you can plus or minus t d3, and that's in the polyhedron for small enough t. That's because it's an extreme point, not an extreme point. So for small t, and okay, so it's the same thing all over again. So either we can perturb infinitely far, actually, in which case we found our line, or we can only go so far, in which case there's some value t3 that we can scale t by, so we can move t only so much up to this value of t3, and we'll activate another constraint, because when you go so far, you've hit another boundary, and hitting a boundary is the same thing as activating a constraint. So you get the idea. So every time you do this, you travel in some new direction, and it's not in the span of the prior ones, and either you can travel infinitely far in that direction, in which case you found your line, or you'll run into a boundary at some point, and that'll activate a constraint. But the claim is that the process has to terminate, and it will find a line. Why? Why does that have to happen? Because otherwise, what would happen if we didn't terminate and find a line? At some point, we're going to keep going and keep going, and at some point, we're going to have this. We're going to have x plus t1 d1 plus t2 d2 plus all the way to tn dn. So we've done this iteration. We've iterated n times. N is the dimension of space that we're working with. Let's call that x bar. Okay, so it's the original x plus, some movement in all these different directions, d1 to dn here, and so that overall point is x bar, and we know that each di is not in the span of the preceding d1 to di minus 1. That's, we've kind of explained that already, because otherwise we would be using those directions and then crossing over a boundary. So we can't be using those directions, because otherwise we would cross over a boundary. So these all have to be new directions that we're going in. So none of the directions are in the span of the preceding ones. And so that means that this collection d1 to dn actually forms a basis of our n, because these are all linearly independent, because they're not, d2 is not in the span of d1, d3 is not in the span of the first two, and so on. And so we're always adding on a linearly independent vector, and then when you do it n times, you've found n linearly independent vectors, so they form a basis for Rn. But even still, we've gotten to this stage, and if we haven't found our line by now, and we're saying we haven't because we can only go to tn distance in this nth direction dn, well, this point x bar that we're finally at now, it's still not extreme. So so there still has to be another direction d prime that we can perturb this point in. So we have x bar, which is that overall point now, plus or minus td prime, the perturbation in the direction of d prime for small t. So we have to be able to do that. But the problem is that d prime could be written as a linear combination of d1 to dn, because the d1 to dn form a basis. So that means that moving in direction d prime corresponds to where we must be moving in some direction di, by some non-zero amount. So we're moving in some direction di, either in the plus or minus case. So so if we are moving in some direction di, we are crossing over the boundary, and then we can't do that because because we're saying we can perturb it, but actually we can't because we'd be crossing over the boundary, and that's a contradiction. So yeah, contradiction that moving in this direction, TIDI activated a constraint. If you go any further, you've now violated the constraint. And so we're getting this contradiction by assuming that we've iterated n times and we still haven't found a line, because then you'd be in the situation. So actually, by the nth iteration, one of these directions must actually be a line that you can move infinitely far in. So this thing means that this d prime can't exist, and so actually the iterating process must actually find a line in one of these directions by the nth iteration. So then that line will of course be in the polyhedron. So that's the proof for that. So what did we just show? Because that was kind of a long proof actually. We just showed that P contains an extreme point if and only if P does not contain a line. Okay, so that is these two things are mutually exclusive, and exactly one occurs. Either an extreme point or a line will be a feature of the polyhedron. Okay, so here is a final fact regarding extreme points. What have we done so far in terms of tests for extreme points? We have a test for a given point in the polyhedron in terms of whether it's an extreme point or not. And that's in terms of this rank of the matrix of tight constraints. And now we just developed another characterization. This characterizes the overall polyhedron. So now we know that we have an extreme point if and only if this feature. We don't contain a line. So we don't know which point is the extreme point. So if we don't contain a line, we don't know which point is the extreme point, but we do know that one exists. Now let's go, so that's the level of the polyhedron, and before we had something at the level of the extreme point, a particular point, I should say, whether or not that particular point is extreme. This is just overall whether we have an extreme point. So this final fact is a geometric characterization of extreme points. We're zooming back into the level of a particular point of the polyhedron, okay? And so we can again test whether or not a point is an extreme point of the polyhedron, a particular point, and but this time it's before that was in terms of the rank of the matrix of tight constraints, that was kind of an algebraic or algorithmic kind of thing. This one's more of a geometric nature. And it's also kind of related back to something in the prior video that you'll see in just a moment. But this will be the final fact for the video. Here it is. So what is the characterization? So x bar, a point in the polyhedron, is an extreme point if and only if there exists some vector C in Rn such that C transpose x bar is strictly better than C transpose y, strictly greater than C transpose y for all y's in the polyhedron, besides x bar, of course. Or in other words, x bar is the unique optimizer of C transpose x. Okay, so imagine we have the polyhedron P, and we can just geometrically test whether or not we have an extreme point. That means that there is some linear program with this polyhedron as the feasible region, and that linear program has this objective function C transpose x, or some objective function C transpose x, where there is only one optimizer, and it is that point x bar. So that's true exactly when x bar is an extreme point. Okay, so let's just talk about it geometrically for just a moment. So let's go back to the example from the prior video. What we had was that this point, it was indeed an extreme point, and it was the unique optimal solution to the linear program that we had. We knew what the feasible region was given by the constraints, and then we wrote down an objective function And that objective function had these green lines as its level curves. And we said that when we pushed those level curves all the way up, we got this one, and it intersected the polyhedron at exactly one point. And since it intersected at exactly one point, and this was as high as you could push, because otherwise you'd be outside the polyhedron, then that was the unique optimal solution. And it was an extreme point as well. And so you can see that this point satisfies this condition, because the vector c in that case, I think it was 2, 3 or something like that. 2, 3 sounds right. The components of c would be 2, 3. But anyways, there was just some objective function that realized this point as the unique optimal solution. That's what happened in the prior video. And so that's just not true for that point, though. It's actually true for any extreme point of the polyhedron. Okay, it's not going to be the same vector c, it's not going to be the same objective function, but there is some objective function which has a unique optimal solution being that particular extreme point. Okay, so you have to imagine that when you have this vector c, you can look at the level curves, because that gives you the function c transpose x, and then the level curves of it, you're trying to push them as high as they can go. And when you push as high as they can go, they should just touch exactly at the extreme point, that single extreme point. And that's why you geometrically see that that it's the unique thing, the unique point that is realized as the optimal solution. Okay, so that was true for this point, but there were 4 other extreme points, right? This one, and that one. So they are also can be realized as the unique optimal solution to some linear program. So for instance, here's an extreme point, another one. So it's in light blue, and if you take the linear program, if you take the objective function so that the level curves of that objective function turn out to be these green lines, you can see that as you push up, at some point you get this one, this level curve, and it'll touch the polyhedron at exactly one point, and it's that extreme point, and then that is the unique optimal solution to the linear program, which has for the objective function has these as the level curves. And how about for this point, this corner point, extreme point? We can, if we have a linear program with these objective, with the objective function with these level curves, then you can see that we realize this point is the unique optimal solution, because this level curve is the best you can do. You push as far as you can, and you get this, and it touches exactly at that corner point, at that extreme point. And same thing. Okay, so you get the idea. So here's an extreme point, and here is a direction you can push level curves in, so that at the end it'll touch exactly at that extreme point, and only at that extreme point. It's the unique point. And same thing here. So that direction might not be unique. There could be multiple C's. There could be multiple objective functions which make that true, but there's at least one. It's guaranteed to exist. So let's prove that. So first, let's prove that if we have some vector c, so it's some objective function now, such that when you such that x bar is the unique optimal solution. So C transpose x bar is strictly better than C transpose y for all the y's that are in the polyhedron except for x bar itself. So let's suppose that's true, and then let's show that x bar is extreme. Why is that true? Well, because if we had this feature that C transpose x bar was strictly better than C transpose y for all those other y's, and x bar was not extreme, well then what we can do is we could write x bar as a it's strictly between two other points, x prime and y prime, that are in the polyhedron. So x bar is lambda x prime plus 1 minus lambda y prime. And then C transpose x bar, we can just replace x bar with that right-hand side, and then you distribute the C transpose in, and you get lambda C transpose x prime plus 1 minus lambda C transpose y prime. But remember, x prime and y prime, these are points that x bar is strictly between. So x prime and y prime are distinct from x bar. They are still in the polyhedron, but they are different points. So that means that C transpose x bar and C transpose y bar, C transpose x prime and C transpose y prime are both strictly less than C transpose x bar, because that's the condition we're assuming by hypothesis. X bar is the unique optimum. So it's strictly better than all the other points. In particular, that's true for x prime and y prime. So these two are strictly less than C transpose x bar. So this overall quantity is strictly less than lambda C transpose x bar plus 1 minus lambda C transpose x bar. And then you can just see that the lambda parts cancel and you're just left with C transpose x bar. Okay, well, what did you just prove? You just proved, I'll say we, we're all doing this together. What did we just prove? We just proved that C transpose x bar is strictly less than itself. That's what we just proved. And that's a contradiction. So that's coming from the fact that we just assumed that x bar was not extreme. We get this contradiction. So actually, x bar must in fact be extreme if that initial condition held. Okay, so now let's just do the other direction, and that'll complete this proof. So now let's start by assuming that x bar is extreme, and then we'll show that there actually exists some vector c that that realizes this condition, that realizes x bar to be the unique optimum. So C transpose x bar is strictly better than C transpose y for all the y's in the polyhedron except for x bar itself. Okay, so we're actually going to find a vector c that works. So first of all, just note that since we're assuming that x bar is extreme for the polyhedron, and let's write down what the polyhedron is. It's the x's in Rn that satisfy some intersection of half spaces, right? So it's just ax is less than or equal to b for some matrix A and some vector b. We don't know what they are, but just so that we have the notation in place. So here's the polyhedron, and x bar is extreme for the polyhedron. So what that means is that the rank of the matrix of tight constraints is full column rank. So n, the dimension of space and the number of columns of the matrix A. That's the rank of the matrix of tight constraints. It's the matrix of tight constraints for this point x bar. So we're looking at the point x bar. What are the tight constraints for that? That's the matrix A equality in question here. Okay, so the rank of that is equal to n, and so what's this vector c that we're going to get? So the claim is actually that c, if I take the vector being the sum of the rows of the matrix of A equality. Okay, so look at the matrix A equality. That's the matrix of tight constraints for x bar, and I sum those row vectors together. So those row vectors are all vectors in Rn. Okay, and so just sum those together, and if you take C to be that works. So that would probably be just a bit difficult to actually find on your own if you're just trying to figure this out on your own for the first time. I'm not sure how quickly this idea might come to you. I don't know how quickly it would come to me either. But anyway, so here's the proof. C transpose x bar. First, let's compute that. So that's so we're saying C is this thing, the sum of the rows of A equality. So it's C transpose x bar is the sum of these row vectors transpose x bar, and remember, this is the matrix of tight constraints for x bar. So that means that when I take a row of that matrix, dot producted with x bar, we're getting exactly it's equal to the component of bi for the equality components. So that's equal at each individual component level, and so for each individual component they're equal. So then when you do the overall sum, they're also equal. So the sum of these things is the sum of the b equality components. Okay, so that's what C transpose x bar comes out to be. It's the sum of the b equality components. Now, how about C transpose y for any generic vector y? It's not necessarily x bar. I haven't yet decided that y is distinct from x bar, but it's just any vector y in the polyhedron. Well, it's the rows of that matrix transposed times y, and we just take the sum of those. Remember that we know that this is a row of the overall matrix. So because this A equality is a submatrix of A, so this is a row of the overall matrix. And for any row of the overall matrix, when you multiply by some vector y in the polyhedron, we know by what the definition of what the polyhedron is, it's a less than or equal to constraint. So for that particular row, whichever row we're looking at, times this feasible vector y, by definition y is in the polyhedron, so then it must satisfy this as a less than or equal to constraint. And the particular constraint we're looking at is a matrix equality constraint coming from x bar. But it doesn't matter, it's just one of the constraints. So then that must mean that it's less than or equal to the corresponding right-hand side. So then the overall sum is less than or equal to the overall sum of the right-hand side components. So, but the sum of these right-hand side components, that's exactly what C transpose x bar worked out to be. So, but this sum of bi's for the equality components is an upper bound for C transpose y for a generic vector y. So what we just showed is that C transpose y is less than or equal to C transpose x bar for all the y's in the polyhedron. Now we want to show that if y is distinct from x bar, then actually it's strictly less than. So let's actually just take a vector y that satisfies equality, okay, such that C transpose y is exactly equal to C transpose x bar. What we're going to find out is actually that must mean that y is the vector x bar. There's no other possibility. Because the reason that happens is because if C transpose y equals C transpose x bar, we know that the matrix equality constraints for x bar, when you take those rows times that vector y, they equal bi for each of those. Because if you look above, we said that each of those components was an upper bound, but we're assuming that overall we are assuming that we've attained the sum, that upper bound being the sum of all those components. So then individually for each of those individual components, we must have also attained that upper bound. So that must actually mean that we've attained this upper bound of bi for each of the individual components for the rows corresponding to the matrix equality constraints for x bar. And so in other words, when you take the overall matrix A equality times y, that is equal to the vector B equality, because it's equal here at the level of each individual component. So when I say all I here, what I mean is all the indices I corresponding to the rows of the matrix of tight constraints. So we have A equality times y is equal to B equality because each of these individual equalities hold. And but we know that A equality x bar equals B equality is the unique solution of A equality x equals B equality, and that's because the rank of that matrix is n. That's what we're assuming. Since we're assuming that x bar is extreme, then we know that the rank of the associated matrix of tight constraints is full column rank. So that in turn means that that the unique solution to this equation is x bar, but we just said that y is also a solution. So actually that means that y is equal to x. Sorry, that's not x, that's x bar. So let me just put a bar there. So y is equal to x bar. Again, a bar. So therefore, if y is distinct from x bar, then actually it must be strictly less than, because it's less than or equal to, and if it were equal to, we just said that they're actually the same point. So if they're different points, then it's strictly less than. So that shows that particular choice of C that we made being the sum of the rows of the matrix of tight constraints corresponding to x bar, that works as realizing x bar is the unique optimal solution to that objective function. Okay, wow, so that was really just a grab bag of fun facts about extreme points, but I think they're all relevant in the context of the prior video, and they're just also facts that it's probably good to know before leaving that topic, because that's what we're about to do. We're about to leave the entire topic of geometry behind for now, because we're about to do the next topic. So the next topic in linear programming is duality. So duality in linear programming is something that I will explain in upcoming videos, and it's absolutely a topic that you can't not know, and it's just very applicable to all sorts of situations. I don't want to say too many words about it right now, but yeah, that'll be for the next video. So look forward to that, and if you have been, thank you for watching this video.